In the last chapter, we looked at K's rule, and there were some other similar kinds of things where we looked at mixtures of substances. And they all were based on mole fractions of the material. Most of us, unless you really are into chemistry, are not very comfortable with moles because moles are a weird thing. They're counting molecules, and we can't see the molecules. We're really much more comfortable with mass because we can measure that. Okay? But we do need to be able to relate moles and mass, and we have the molecular weight or molecular mass of a substance that will allow us to do that. So just to kind of remind us of some things that we knew one time when we took a chemistry class, let's just look at a really simple little problem here. I have 20 grams of ethanol and 60 grams of water, and they're mixed together. Okay? And so if I look at this, the masses, I have 20 and 60, so I have 80 grams total. And 20 of those 80 grams are ethanol. So this mixture is 25% ethanol by mass. But I could also do this on a mole basis. And so for that I need the molecular mass. Ethanol has a molecular mass of 46. Water has a molecular mass of 18. Now, the way we were taught this in chemistry is the units on this are grams per mole. It's how many grams an Avogadro's number's worth of molecules would weigh. And so to take the mass that I was given and divide by the molecular mass gives me the number of moles I have of the substance. So in the case of the ethanol, I have 0.4 moles of ethanol. In the case of the water, I have 3.3 moles of the water, meaning I have 3.7 moles total. 0.4 divided by the 3.7 means it's 11.5% ethanol by mole. So we see that we're going to get different values between the mole fraction and mass fraction. We know that we were instructed in the previous chapter to use mole fractions. Let's see if we can get a little bit more comfortable with that, have a little bit of a deeper understanding about how these things work. So first, let's talk about these moles. So in chemistry, you were taught Avogadro's number, 6.02 times 10 to the 23rd. Molecules of a substance is called a mole. And so many grams per mole is the molecular mass of the substance. And so we have like hydrogen has a molecular mass of 2 and water a molecular mass of 18. And the implied units there were always gram per mole. But for engineering purposes, this is a really bizarre and inconvenient unit. Okay, first of all, grams. Grams are teeny tiny for things that we do on an engineering scale. We never deal with grams. Kilograms, maybe. Even that's frequently a small quantity for engineering. So usually what we do is we say, well, what are the mass units I like to work with? So we'll say kilograms and pounds mass if I'm in engineering units or if I'm in SI units. So I define a mole for that particular mass unit so that the molecular mass is the same. Okay? So the molecular mass M could be units of grams per mole or kilograms per kilogram mole. Now, kilogram is just 10 to the third times a gram, right? So a kilomole or kilogram mole is 10 to the third times a mole. So this means that if I'm using kilogram moles, then it's 6.02 times 10 to the 26th molecules of a substance, adding 3 here. But I could also do this for pound mass. So if I have pound mass, it's a pound mole. Now the exact number of these things is a little more complicated because remember, a pound mass to a gram I have 454 grams in a pound mass. So that means I'm going to have to do something with that 454 to get to my pound mole. But usually I really don't care, just as long as I can be consistent about which type of mole I'm using. So I put a prefix on the word mole to match the mass unit that I'm really using. And as long as I use that throughout a problem, it's no big deal. So let's just take this, a 50-pound mass sample of water. How many pound moles is this? Well, molecular mass of water is 18. Okay. Normally I think grams per mole, but now I want to use pound mass, so it's pound mass per pound mole. Therefore, I want to divide in order for my pounds mass to cancel. 50-pound mass of water divided by 18 pound mass per pound mole of water tells me that I have 2.8 pound moles of water. Okay, so how about if I do something just a little bit more complicated units? Okay, I have water flowing at 75 kilomoles per second. I want to know the mass flow rate. Again, use the molecular mass. Still 18, but this time it's kilograms per kilogram mole. And so therefore 75 kilomoles per second times 18 kilograms per kilomole. My kilomoles will cancel. Convert my seconds to hours. 3,600 seconds is 1 hour. And I get 4.9 million kilograms per hour. Now, I also am going to need to deal with mass fractions and mole fractions, or mass percent, mole percent, in a lot of different problem settings. And one of the things I find most helpful is to always treat these things with their units. So let's just look at this briefly. If I have the mass fraction or mass percent of a substance, I use X sub A. Your textbook uses MF sub A. But X sub A is the mass of substance A divided by the total mass of the mixture. YA is the mole fraction. It's the total moles of A divided by the total moles of the mixture. And this looks like they ought to be dimensionless. So if I had 3 kilograms of A and 10 kilograms total, then it's 0.3, and kilograms per kilogram cancel out, correct? But when I'm actually solving problems, I find that I have less confusion if I treat it as if it has units. So it's 3 kilograms of A divided by 10 kilograms of mixture is 0.3 kilograms of A per kilogram of mixture. By doing that, I can actually more successfully solve problems. So let's just look at a couple of very quick ones here. I have a solution flowing in a tank at a rate of 58.3 kilograms per hour. This solution is 23 mass percent water. And so I want to know what the rate that water flows into the tank will be. So 58.3 kilograms of solution per hour is multiplied by 0.23 kilograms of water per kilogram of solution. Now it's very easy to see that the kilograms of solution cancel, leaving me with kilograms of water. So I have 13 kilograms of water per hour. Similarly, if I had 10 pound moles of water flowing in a solution that's 43 mole percent water, okay, so this is just the pure water, but it's in a solution that's 43% water, then I'm going to say 10 pound moles of water per second. It's 43 pound moles of water per pound mole solution. That means I want to divide by 0.43 pound moles of water, pound mole solution. Pound moles of water cancel. I'm left with 23 pound moles of solution per second. Okay, so see there how you can make units work to your advantage if you remember to write them down whenever you deal with mass fractions or mole fractions. Now we're going to pause there and come back in the next lesson and talk about mole fraction and mass fraction and how we can relate these two.